Hey everyone, my name is Noah, and today I will be presenting on uniform differentiability and exercise 5.2.8. So we'll start with the definition. Given a differentiable function f from a to the real numbers, let's say that f is uniformly differentiable on a if, given any epsilon challenge, there exists a delta greater than 0, such that 0 less than x minus y less than delta implies this inequality f of x minus f of y over x minus y minus f prime of y is less than epsilon. So recall we did talk about uniform continuity in class, which has a similar definition, although the implication is slightly different. But having this definition here, I thought might be a little helpful. Moving to part A, we're tasked to find whether x squared is uniformly differentiable on all real numbers, and then whether g of x equals x cubed is differentiable on all real numbers. So we can start with x squared and we're reframed for any given epsilon greater than 0, does there exist a delta greater than 0 such that this inequality is true whenever we have this, right? So now we can do some scratch work. We first need an expression for f prime of y. We can use the power rule from example 5.2.2 to get that the derivative of x squared is 2x, something we learned in Calc 1, and then substitute in for f prime of y equaling 2y. We can then use the difference of squares here and substitute in, simplify down to absolute value of x minus y less than epsilon. And remember, we can manipulate that with the use of delta and select delta equals epsilon. And you see with our formal proof, we simplify down and see that this is less than epsilon for arbitrary epsilon. So we conclude that x squared is uniformly differentiable on all real numbers. Move to x cubed now. And so we reframe this again, and we see a very similar inequality or a similar implication just with x cubed and y cubed. So again, we need an expression for f prime of y. And again, we can use the power rule from the same example and see that f prime of y is going to be 3y squared. So helpful equality here is going to be the difference of cubes. A little tricky, but we can use that to help simplify in this situation. So we use the difference of cubes and our expression for f prime of y to find this expression here, which equates to absolute value of x minus y times the absolute value of x plus 2y less than epsilon. Here we run into a problem. We can make absolute value of x minus y as small as we want with the manipulation of delta. However, we have no ability to place a bound on x plus 2y as we are considering all real numbers. If you remember from the continuity example in class, we were only considering a bounded interval or closed interval, which allowed us to put bounds on x and y, but we can't do that here. So this can be greater than epsilon because we can select x and y that are large enough for that to be true. So x cubed is not uniformly differentiable on all real numbers. Next, we need to show that if a function is uniformly differentiable on an interval a, then the derivative must be continuous in it. So we're given that a function is uniformly differentiable. That's the definition here. We need to find that the derivative is continuous in a. So we need to find that f prime minus f prime of y is less than epsilon for a given delta. So now we can start with our given. Let f be a function on the interval a to the real numbers, and let delta be delta 1, such that uniform differentiability is true with f of x minus fy less than epsilon over 2. We'll get to why we need to use that later. So we do some scratch work because we need to get f prime of x into the inequality. So we're going to start by adding 0 into the absolute value signs creatively by inserting this expression minus plus that cancels out. And then we know by the triangle inequality here that we can separate them, that this expression is going to be less than or equal to the addition of these two terms. We can also reframe this term here and switch the terms around as the subtraction sign and the absolute value sign allows us to do this. So now we can select a delta 2 such that x minus y, which is the same thing as y minus x, implies that this now is less than epsilon over 2. Remember, this looks very similar to our initial statement, but instead of f prime of y, it's f prime of x. As you can see, we just flip the terms around. So now we can select a delta, which is the minimum of those two delta values. And that will guarantee that both of these inequalities are true. And that's where we can step forward. We can now show that f prime of x minus f prime of y less than or equal to these two terms, which are less than epsilon over 2, epsilon over 2, which is just epsilon. So include that a function that is uniformly differentiable on an interval must also have a continuous derivative on the interval. So now moving to part C, we're looking for a theorem analogous to theorem 4.4.7 for differentiation. We can see that theorem down here. And so we're basically looking for if the functions that are differentiable in a closed interval are necessarily uniformly differentiable. So we can look back at the contrapositive of part B to help us here. So that statement is going to appear if f prime is not continuous on the interval A, then the function f is not uniformly differentiable on the interval A. Thus, it remains to find a counterexample function denoted f, which satisfies two things. F is differentiable on a closed interval, and f prime is not continuous on this interval. So we consider the example from the textbook, f of x equals the piecewise function x squared sine of 1 over x at all points except 0, and then it's defined at 0 as when x equals 0. So on the interval, including -1 to 1. The only point that would seem as if not differentiable would be the point x equals 0. We see that f prime of 0 using the limit definition equals 0. So we use the chain rule and the product rule now to find f prime of x equals negative cosine 1 over x plus 2x sine of 1 over x. So we know that the function is differentiable at all points in this interval. So we need to find that it's not continuous now. So we must find a sequence in the domain that converges to 0, but does not, but the image of the sequence does not converge to f prime of 0, which we've already found was 0. So we consider the sequence x of n, which equals 1 over n, which converges to 0. When we consider f prime of x of n, it simplifies down to negative cosine of n as 2 over n. This, when going further out, becomes 0, so this term goes away. So we only have negative cosine of n, and this will bounce between -1 and 1, right? So we know that f prime of x of n is going to diverge. So f prime of x is not continuous at x equals 0 because we're able to find the sequence. Therefore, we conclude that it is not necessarily true that functions that are differentiable on a closed interval are also uniformly differentiable.